Hey guys, welcome back to CMTEQ channel. This is tutorial 5 on our series of tutorial on short circuit calculations. In other words, fault current calculations. Now in this tutorial, we've got a network, okay, that is made of a generator and two transformer T1 and T2 that are coupled in parallel, okay, and they are feeding a feeder line into a substation. So this one will be a distribution substation that is going to go through different areas. And on my right here, I've got an illustration. As you can see, there is a generator G1, T1, transformer, and T2, and then we've got our feeder and the substation right there. Now, before we can start discussing how to solve this tutorial on our fault current calculations, they are asking us to discuss the various types of fault which can occur on the distribution system below, because this is a distribution system that is made of a generating substation, two transformers that are stepping up, and the feeder line, which is a transmission line, and you then have your distribution substation right there. Now, to discuss the various types of fault that can occur in the system, so first of all, you just have to understand that it's a three-phase system, okay? Like in my right side here, I've illustrated here making just a one wire, but this is actually a three-phase system. So you got three wires coming out of a generator, actually with the fourth one for the neutral. And we also have the one running into the transformers, and also the feeder is a three-phase system. That basically means, because it's a three-phase system, so we can have single phasing. Single phasing is a type of fault that occurs when you have either two phases that are shorting with one another, or you got all the three phases shorting together. So that's create a single phasing. So that's one of the fault that can occur. And we can also get a short circuit in the transformer. The other fault we can also get is a short circuit inside the transformer winding. So like T1 and T2 here, they've got winding that's a primary and secondary winding. So you can get those two windings short circuited, and that can also create a fault. So that is fault number 2. What else can we get? Now we've got a feeder. A feeder is a transmission line. Of anything can happen. Your pylons can fall, or your cables can short, and all sorts of things can happen. You can get a feeder fault. You can get a feeder fault of that nature. And also on your distribution substation here, in case of overloading the system, your feeder was designed to carry, let's say, a load of 60 MVA, as you can see here. But now all of a sudden, your substation, you are feeding something here, you are feeding one more thing here and another one here. So you got three loads. So you've got three different loads that are being fed. And all of a sudden, you've got more loads that are connected that were not supposed to be connected to this substation. So what will happen is this feeder will be overloaded. And that can also create a type of situation that is not pleasant, which is also a fault. So those are some of the things that can occur, but obviously many more things can happen. And please, if you're going to try to develop them and discuss those issues, drop a comment in the comment box below, and let me know if you have any question or anything on discussing this type of fault. Okay, so now we're going to move on and solve the problem, because that's what we are here to do, to solve for the fault current. Now, before we do that, please don't forget to subscribe to CMTEQ channel and give this tutorial a thumbs up. That will be highly appreciated. You are also welcome to share it with some of your fellow students. Okay, now they say we need to calculate a short circuit current, okay, fault MVA in each case for symmetrical, okay, three-phase short circuit at F1 and F2. So this is F2 right here, and this is F1. Now we can clearly see that F2 is a fault that is occurring right before the transmission, and F1 is occurring after the transmission. So we need to see the magnitude of this fault. Obviously, the transmission impedance is going to determine the difference between these two faults. Okay, now moving on for our solution. Now you'll understand that in order for you to be able to understand these problems, because this is per unit system, okay? So you have to understand the per unit system. Why? Because we need first to convert this network into a per unit impedance. That's why per unit is very important. Now, in order to convert these network, these electrical quantities of a G generator, T1, T2, and the transmission line, the feeder, into an equivalent impedance, we use a per unit formula, and that is given by this general formula. Now, if you are not too sure of how this formula work, I've done a lot of tutorial on this per unit system, so you can go and look up in my channel on the per unit playlist. Okay, so basically we're just going to implement this formula to find the new per unit of the generator 1, T1, T2, and also of the feeder. So moving on, so for generator 1, we got Z per unit new, that is 0.15, so that is the old one if you look at the formula, and we've now selected the base MVA to be 80 MVA. Now that is very crucial. We've selected the base MVA to be 80 MVA. And you have to make sure that you maintain the 80 MVA throughout the entire calculations of this problem. Because if you use a different one, then you know you're going to get a wrong value. So 80 MVA, that is the generator MVA, is now the new base MVA for the entire system. So we find that we got 0.15 J per unit for G1. Now moving on, T1 we got 0.1 J per unit. And T2 we got 0.1 J per unit. And you can clearly see that T1 and T2, they got exactly the same parameters. They are both 40 MVA, which is the old MVA, and 5% of the old per unit. Applying the formula, we get that, and we understand that the two transformers are receiving, the primary here is 33 kilovolt because the generator is generating a 33 kilovolt three-phase system. Okay, so now everything is clear. If you have any question, please don't forget to drop your comment on the comment box. Okay, moving on. So we're going to now calculate for the feeder line. Now, the feeder line, as we've already stated, is a transmission line, but it has its own parameters, and it is now rated for that 60 MVA and also transmitting at 88 kilovolt. Why is it transmitting at 88 kilovolt? Because precisely the two transformers here are stepping up the voltage from the 33 of the generator. So which means this zone here, the entire transmission zone here, is 88 kilovolt, the potential there. Now, there is a formula that you can use to calculate the voltage of the zone, because that is very important while dealing with these issues. You know the base MVA, okay, and you use that for all your calculations, but it is also important to remember the base voltage, because the zone voltage rather applies on each and every zone. For instance, on this zone of G1, T1 and T2, we got 33 kilovolt. But on T1, T2 to the feeder substation here, there is a 88 kilovolt. Now, if you are unclear, you all need to do just to apply this formula. That is for VB zone. Okay, that's the one that we need to find, is equal to VB of the previous zone times the transformer, because remember, we go from the primary to the secondary of the transformer. That's what determines the zone voltage. Now, so that will then be the ratio of the secondary over the primary. Now, applying this formula will mean the previous zone is 33 kilovolt. Now, we've got the secondary, that is 88 kilovolt, and the primary, which is 33 kilovolt. And cancelling these two here, we got the 88 kilovolt. So that means that this zone here is 88 kilovolt. But you might find a situation where the secondary of the transformer is different, but the zone voltage is also different. So you need to apply this formula so you can get the correct zone voltage. Those are usually, those kind of traps are placed when it's an exam problems, because they want to know if you understand these things. Now we know what is the voltage zone on our feeder, so we can then go ahead and calculate the per unit value of our feeder. Now remember, we've got the old per unit there, that is 6.75%. That is the value there. And then we've got our new base impedance of 80 MVA that we said, and the 60 MVA that is represented there, and the 88 kilovolt over the 88 kilovolt, because that's the old and the new is exactly the same thing. And again, here we are just applying the per unit formula. So we found 0.09 J per unit. Now we move on. So what the next thing to do here? We need to redraw the circuit for the fault at F1. Okay. Now we can choose to do the F2. It doesn't matter really because they are independent. They are not occurring at the same time. But we are now first calculating for F1. So we need to redraw our circuit. So what it means is that we got the generator. And then we've got the generator per unit, okay? And then we've got the transformer 1, transformer 2, and then we've got our feeder also per unit. Then we can't draw the substation because now there is a short circuit at F1. That means power is running from the generator like that through this transformer, through here, and through the ground. And that's exactly what's going to happen. So which means all we have to do now is to calculate the total per unit impedance based on the trajectory that the current or power is going to take based on the formula. So in order to do that, we are going to simplify this. So this is just now a resistive network that you need to reduce. And that is very simple. So Z per unit total is going to be equal to this impedance plus parallel network, so that's going to be 0.1 times 0.1 over 0.1 plus 0.1 plus 0.09. That is this one. So this is the equivalent per unit of the network. And the value for that will be Z per unit total is going to be 0.29 J per unit. Okay, so now that we've calculated the Z per unit total, the next thing to do is to calculate the short circuit current based on the per unit impedance of this entire network based on where the fault is located. So our short circuit will then be equal to I per unit times the I line. Now what is the I line? That is a very good question. But what is I per unit also? Now I per unit is calculated by using 1 over Z per unit total, because what is I per unit? Now, if you've watched the per unit tutorial, you understand how to calculate I per unit. We calculate it using I per unit is equal to 1 over Z per unit total. This is based on the unity of the per unit system. So, the 1 here represents the 1 volt unit, okay, over the Z per unit total. And that gives us a current of 3,448 amps. You just have to confirm this with your calculator if you are following along. So now that we've calculated the I per unit, so the next thing to do is then to calculate I line here so that we can then finally calculate our short circuit current. Now the I line is given by the formula. I line is SB nu divided by VB zone times the square root of 3. Now remember, now this is very interesting, this VB zone, because you have now to know where the fault is located. Because the fault is located here at the feeder, so the zone voltage there is also the 88 kilovolts. So that's where your VB zone will come from with your 80 MVA SB nu. And then you find a value of I line of 524.86 amps. And that basically will mean that your I short circuit current will be that current there, the I per unit times your I line, and that gives you 1.81 kilo amps of current. So that's your I short circuit. So that's a short circuit current that is located here at F1. And obviously, you're now going to use that short circuit current to calculate the fault MVA or your short circuit MVA based on the short circuit current. And again, you're going to use the same formula that you use to calculate your I line, and then to deduce that formula by replacing I line with your I short circuit current, as you can see here. So your short circuit MVA will then be the square root of 3 times the VB zone times your I short circuit, and all of that is going to give you a 276 MVA or megavolt ampere of your short circuit current. So that is how we calculate here on the fault 1. Now we're going to move on and then calculate the short circuit current and the MVA for fault 2. So moving on, we're then going to continue, and then we're going to redraw the circuit for the fault on F2. Because now we already calculated the per unit, so we're not going to do that again. we're just going to redraw, but this time our fault is now located at the section here. Redrawing our circuit, we then get the same circuit, but this time we have excluded the feeder, because when the short circuit occurred at F2 here, this entire section is now removed from the path where the current is traveling. So that means the current is not traveling from the generator, okay, through T1 into the line down into our fault here. It's not even going into the transmission line because the fault is occurring right there. And another trajectory the current is taking is this one here into the fault. So this is the path where the current is taking right there, like that. So now we need to now calculate the magnitude of this short circuit current and the short circuit MVA. Now moving on again, we're going to use the same procedure as the previous one. So based on our current circuit and the path the current is taking, we can then deduce the Z per unit total as we did in the previous section. But this time it is equal to 0.2 J per unit. And as you can see, we don't have the section of the feeder. That's why the value is only 0.2 J per unit. And again, from here, we follow the same procedure. Our I per unit is 1 over Z per unit total, and that gives us a 5 amps. Notice how the current here, the per unit current is higher compared to the previous per unit current. So the previous per unit current was slightly lower than this one because we had an impedance here that was dropping the current slightly. Okay, that was the feeder impedance. Okay, now moving on, we then going to look for the line. So our line is also going to be I line over SB new. Our line current is going to be I line is equal to SB new over VB zone times the square root of 3. This is also going to be exactly the same 88 kilovolt because up from this side here all the way to here, it's the same 88 kilovolt that is the potential voltage there. So that is going to be exactly the same I line current, that is 524.86 amps. All right, so now moving on, the equation become much simpler. We can then calculate our I short circuit, that is just multiplying the I line times 5, and that gives us a current of 2.6 kilo. And from there, it will be much easier to now deduce the MVA short circuit. So our short circuit is then going to be equal to the short circuit MVA over the VB zone times the square root of 3. From there, we can then pull our short circuit MVA is equal to this expression, and replacing, we find the short circuit MVA of 400 megavolt ampere. And as you can see, just by removing the feeder, making the fault to be at this point here, we got a higher fault current and a higher megavolt ampere fault level. And that is exactly the reason why per unit is very much important. This is why they actually sometimes place what you call it reactors. So reactors are used to dampen the short circuit current to a level that is acceptable, because when you have two generator couples between one another, you're going to have a higher fault current. Now to reduce that, you put reactors in between so that you can, because a reactor will introduce an impedance just like this feeder impedance here, and that's going to reduce the fault current on that particular line. There is many other methods that can be used, but for now let's just conclude this tutorial here. And please don't forget to subscribe to CMTEQ channel and give this tutorial a thumbs up. Stay tuned for more per unit, more short circuit current tutorial like this in the coming days. Cheers.